Let us consider problem 7.65 of Sonntag, in which it is proposed to build a 1000 megawatt electric power plant with steam. Okay, condensers are cooled with river water. So the figure drawn in the book, something of this sort. There's a so the river sort of flows in, the river flows out. So the mean velocity is equal to 10 meter per minute, and the cross section area of the river is equal to 60 by 8 meters. So the volumetric flux, let me call it as, so the mass flux in the river is equal to the density multiplied by the volumetric flux, which is equal to density multiplied by 60 into 8, which is the cross section area, multiplied by the velocity, which is 10 meter per minute. So this is meters per second. Okay, so the density of water is 10 raised to 3 kg per meter cubed. 8 into 10 raised to 4 kg per second. So m dot river is equal to 8 into 10 raised to 4 kg per second. So let me just quickly rub this off. It's just a part of it. So the idea behind the problem is, the pressure in the condenser is given. We are given the maximum temperature of the boiler. The pressure of the condenser should correspond to a temperature in the condenser, because the things in the condenser are in the two-phase zone. Okay, if we assume everything to be a Carnot cycle, things are very easy, because we can then relate the temperatures to the works done. So the operation temperature of steam, so this is the boiler, so this guy is at 550 degrees Celsius. So there is a pump, there's a condenser, and there's a turbine. So this temperature is given as 500 degrees Celsius. It is given that the pressure in that condenser is equal to 10 kilopascal. So we must find out the corresponding saturation temperature corresponding to this condenser pressure. So TL is equal to temperature of steam at T equal to 10 and X equal to 1. TH is given as 550 degrees Celsius, so I had 273.16. Similarly, because this temperature will be in degrees Celsius, I have to add 273.16. So these are the temperatures. So the condenser is the part which is exchanging heat with the river. So first of all, this is the total work output of the cycle, including whatever little work the pump takes. So the work is equal to 1000 megawatt. So QL is to be found out. So the QL divided by the work is equal to TL divided by TH minus TL. This is as per the Kelvin's proposition, that for Carnot cycle QH by QL is equal to TH by TL. So we have simply modified a part of this and written, instead of QH and QL, we have written QL and work. It's very easy to write in terms of the temperatures. So all the temperatures must be reported in Kelvin, otherwise it will yield an error. Temperatures are in Kelvin. Okay, so the work is given. Now we can find out what the amount of heat transfer QL is equal to. The QL is found out to be 632.6 megawatt. Okay, because work was in megawatt, it was 1000 megawatts, so QL is in megawatt. So now the amount of heat transferred is equal to mass flow rate, which is 8 into 1e4. So because this is in megawatt, let me multiply by 1e6 to convert it into watt. So this is the kg per second multiplied by the specific heat. So P equal to 10 multiplied by delta T. Okay, so for the specific heat we must specify the two quantities. So it is specific heat of water. Okay, this must be the specific heat of water in the river, which must be at 100 kilopascal and x equal to 0, saturated liquid. Okay, so the delta T, okay, there's a small mistake once again, because the specific heat is in kilojoule. Okay, so the fundamental property is, this guy was in joule, this guy was in kg per second, this guy was in kilojoule per kg. So that is why we must convert it from kilojoule to joule. Okay, so the temperature rise is found out to be 1.875 degrees Celsius. It's very important to keep in mind the physical insight, because obviously without writing down this kilojoule, we obtained a very absurd answer. If I delete this, we see that the answer was rather absurd. It was 1875. That cannot be the temperature rise in a river. Okay, so this has to be multiplied by 1e3. Okay, so for convenience, let me just take this over here. So this QL was found in megawatt, this was in kg per second, but the output of the specific heat function is in kilojoule per kg Kelvin. So to convert the kilojoule into normal joule, so to convert this megawatt, we had multiplied by 10⁶, so this simply became watt. After multiplying by 10⁵, this whole thing became kilojoule per kg Kelvin. This yielded us the value of the delta T. So the temperature rise of the river is around 2 degrees Celsius, which is quite a lot, considering that many geochemical reactions and environmental balances depend very much on the equilibrium of the temperature of the river water. For example, the cycle of salmon fishes, it depends very strongly on how the temperature of the river water is fluctuating. So always keep an eye on the unit, keep an eye on the answer that you obtain, because that will give you insight into where you might be going wrong. Usually, usually if the concept is there, the only source of mistake is by calling internal inbuilt functions and not converting them to the appropriate units. It may not be always required, but in this case, since we had converted the megawatt into watt, we cannot let kilojoule be there, we have to convert it into joule.